Welcome back, Math 30-1, to your third lesson in applications of exponential and logarithmic functions. In today's lesson, we're going to be looking at exponential growth or exponential decay. So in general, whenever we're looking at exponential growth and decay, we're going to be looking at this formula here. Okay? So here we go. It says in 2012, the university population of a country was 160,000 and was increasing at an annual rate of 4.5%. So right here it wants us to find the values for A and B in this equation. Well, A is my initial population. A is equal to 160,000. Okay? And B is going to be my increase. B is equal to, well, what is my increase? 1.045. It's very similar to the investment thing with compounding interest. Now, write an equation to represent the university population P of the country as a function in the number of years, so on. So, population P is equal to 160,000, okay? 1.04, because we increased 4.5, increased by 4.5% to the power of n, okay? Determine the population in the year 2015. Well, our starting year was 2012, so now we want to find the year 2015. My n is going to be equal to 3. So that's just equal to 160,000 multiplied by 1.045 to the power of 3. Now I plug that into my calculator, multiply that all together, I'm going to end up getting 182,587. Okay? There we go. Now the next one says, determine if the population continues to grow at this rate, determine the number of years to the nearest year for the population to double from 2012. So we want to know when the population doubles. So when this doubles, so that's going to be 3, 2, 0, 1, 2, 3 is equal to 1, 6, 0, 1, 2, 3. And we have 1.045 to the n. Now we want to figure out that n here. So first thing I'm going to do is divide this by that. Well, we know it's 2. Because we want to know what, we want to multiply this by 2. Right? That's essentially this. So we want this to equal to 2. So we have 1.045 to the power of n must equal to 2. So how am I going to solve this? I want to log it. Last time I logged both sides. This time I'm just going to use my inverse log. So we go log base 1.045. And 2 is equal to n, or n is equal to that, right? Now, what does this simplify if I want to put in my calculator? We just go log 2 divided by log 1.045 is equal to n. Plug that in, and I'm going to get 15.74. Okay, plug into your calculator, and you get 15.74. So in general, in order for the population to double, it's going to take approximately 16 years. So that's going to be in the year 2028 will be the year. Okay? Because it'll take 16 years from now. All right. Here we go. Class example number 2 says the number of fish in a lake is decreasing by 5% each year as a result of overfishing. So if the number of fish present is an exponential function of time, state the base of the exponential function. Well, my base, so my base is, when we're looking at y is equal to a, b to the x, we want to figure out what b is. Well, we're going down 5% each year, so that's 1 minus 0.05, which gives me 0.95 is my base, because we're only going to have 95% of the population each year, so we're always exponentially decreasing, so that's decreasing there, okay? Now, write an equation for the number of fish present after t years, okay? All right, we use n to replace the initial population and nt to replace the final population. Okay, so we want to write an equation to represent the number of fish present after t years. So final population, we're going to use nt. My initial population is n naught. Oh, doesn't tell us. And we have 0.95 to the power of t. Okay? Now, if there were 2,500 fish present in June 2012, how many would you expect to be present in June 2017? Well, I know now m naught is equal to 2,500. Okay? And I know my t is equal to, that's 5 years difference. 5. All right, so let's plug all of these into this formula that we have up there. So we're going to have mt is equal to 2,500, okay, multiplied by 0.95 to the power of 5. So let's put this in my calculator, 0.95 to the power of 5, and I'm going to multiply that by 2,500. And I'm going to end up getting 1,934. Now I'm going to say 35 because we can't have part of the fish. Okay? So there we go. Now let's take a look at D. It says, how many years to the nearest tenth would it take for the fish population to reduce to half the number in June 2012? Actually, this one here we could have rounded down. We could have put 34. I might have been smarter. So how many years to the nearest tenth would it take the fish population to reduce to half the number? So we want, basically, we want this here to be 1/2. Because whatever, we're going to multiply this by 1/2 to get that number. So I want 1 over 2 is equal to 0.95 to the power of t. Well, what am I going to do? I'm going to put this in log form. I can log both sides. So I'm going to log both sides this time. Log 1 over 2 is equal to t log 0.95. There we go. We are able to put the t down. So we get log 0.5 divided by log 0.95, which will give me, put this in my calculator. Let's take a look. We have log 0.5 bracket divided by log 0.95 bracket, enter, 13.5 years to the nearest tenth. So 13.5 years. Okay, so it's kind of like 13 and a half years, you could say. All right, here we go. Now, the intensity, let's take a look at example number 3. It says the intensity of a light source is reduced after passing through d meters of fog. So here is my formula. At what distance to the nearest hundredth of a meter will the intensity be reduced to 1/4 of the value? So here's my I. So if I want this, and that's 1/4. So this is going to be 1 over 4. Okay, so in other words, if this will be 1 is equal to 4, because it's 1/4 e to the negative 0.12 d. Okay, so we have 1 over 4. Okay, there we go. We have that. Now, I could do this in many ways. All right, I could use the natural logarithm, or I could just log it. So I'm going to, for this one, look at it. This is base e. So if we're going base e, I could say log e 1 over 4 is equal to 0.12 d, negative. But log base e is the same thing as ln 1 over 4 is equal to negative 0.12 d. Okay? So I'm going to end up having negative all divided by 0.12 is equal to d. Let's plug that in. So here we go. Negative log 1 divided by 4, or 0.25. And I'm going to, what are we going to do? Divide that by 0.12. And I'm going to end up getting 11.55. Okay? So to the nearest hundredth of a meter, so that's 11.55 meters. All right? So this one here, I use my log formula. This one here, I log both sides. This one, I use my log identity to convert. All right? And it was in base E, so then I just put it in natural log. So now we're going to look at half-life and doubling time. So I kind of started at half-life and doubling time. We're going to look at this formula here and get a little bit closer and more acquainted with it. So first of all, I'm going to try and explain this formula, okay? So this here normally stands for our time to half or double, okay? So how long it takes to half or double. This is the doubling period. It's the time for that. This here is either going to be 1 over 2 or it's going to be 2. Depends if we want it the doubling or half. And this tells us how long it takes to do that. I'll explain to you with our first example here. And this is my initial, this is my final. Okay? So it says, a patient feeling ill had a sample of bacteria taken from her throat. The sample contained 387 cells. 24 hours later, the sample was recounted and found that it contained 812 cells. So 8,012 cells. Find the doubling period of the bacteria to the nearest tenth of an hour. All right. So we want to find the doubling period here. So we know it is a doubling period. So we're going to say this value is equal to 2. Okay, so C is equal to 2. Now, my initial is 387. So let's put that. A naught is equal to 387. Okay? Now, my final, after time, is equal to 8,012. Now, we want to find out how long it took to double. Okay, so 24 hours. In 24 hours, it doubled. It did that. So this is my T, or in this case, they want my period. So my time is 24. T is equal to 24. My period to double is equal to my question mark. Okay? Because basically, we want to know how many times this doubled to get there. So we had 24 hours, we're trying to find, we divide that by something that tells us how many times it will double. Okay, so how many doubling periods it happened. So we continue this here, and I'm going to end up getting, I'm going to move it over here. We have 800 because my unknown is the exponent, so I'm going to isolate for exponent best I can. With 8,012 divided by 387 is equal to 2 to the power of 24 all over p. All right? Now, I'm going to have to log both sides. So I'm going to log is equal to 24 divided by p, and we have 2. Oops, log 2. Sorry, I have to log it to bring that down, right? Log 2. Now, I'm going to divide this by log 2. So I'm going to end up getting, here we go, log 8024 all over 387 all over log 2. Okay, in other words, this is base 2 log that, right? Essentially, that's what we're saying, which is equal to 24 divided by p. But this is nice because we can plug that into our calculator. And when I plug that into my calculator, I'm going to get, and when I plug on my calculator, I'm going to end up getting, so we have log 8024 divided by 387, bracket, and we're going to divide that by log 2, okay? So I get 4.377. I'm going to store this as x, so I know that. So I have 4.37 is equal to 24 divided by p. Now I must solve for p. So I'm going to just cross multiply. So p is equal to 24 divided by that 4.37. Okay? Well, I go 24 divided by second answer. I'm going to end up getting 5.5. 5.5 hours is my doubling period. Okay, so it takes 5.5 hours for it to double. All right, next question. It says, in April 1986, a nuclear accident in Chernobyl contaminated the atmosphere with quantities of radioactive iodine-131. If the half-life is 8.1 days, determine the number of days to the nearest day it took for the level of radiation to reduce to 2%. Okay, so that's interesting. So now I know here we want my A final to be equal to 2%. My A initial is 100% because we started off at 100%, right? I want my final to be 2%. Then we also know here we're looking at half-life. So my C is equal to 1 over 2. Okay? What else do we know here? We're looking at half-life. So I'm going 1 over 2. I have 100% is equal to 2%. Now we know my half-life time is 8.1 days. So P is equal to 8.1. And we're trying to find my T. So we have something over 8.1, and we have my T there. That's how we set it up. Okay. Well, I'm going to isolate that best I can, so I'm going to get 0.02 is equal to all right. Now, I'm going to log both sides, or actually this one here I log both sides, so this one I'm going to use my log identity. So we're going to have T all over 8.1 is equal to log, because remember we're solving for that, base 1 over 2 and to the 0.02, which is the same thing as log 0.02 all over log 1 over 2. Okay, so let's plug that in, see what we end up getting. So we have log 0.02, and we want to divide that by log 0.5. All right, and what do I end up getting? I get 5.64. Okay, so this is equal to, so we have T all over 8.1 is equal to 5.64. All right, now we have to solve for T, so I'm going to multiply that by 8.1. And I'm going to end up getting 45.7 years. To the, okay, so it took radiation to 2% of the original level. Determine the number of days to the nearest day. Okay, so it's going to be is 8.1. Okay, so 45, so 46 days, because we have to round up, so it's going to be 46 days. And that's how long it took. Okay, and there we go, done. So example number 6 says, a radioactive isotope has a half-life of 7 years. Okay, so use the formula given here with C is equal to 1/2 to determine how much of the isotope must be present to decay to 60 grams. All right, so we want to know how much decays to 60 grams. Well, we know my A final is equal to 60. We don't, my A initial is what we do not know. Okay, that's something we do not know. We know my time is equal to 14. We know my period is equal to 7. Okay, and we know C is 1/2. So let's take a look at this. We're going to have 60 is equal to A naught, and we have multiplied by 1 over 2 all to the power of 14 divided by 7. Okay, so that's going to be 60 is equal to A naught, and this is going to be 1 over 2 to the power of 2. All right, we square that, and I get 60. So then I have to multiply this by 4. Oops, A naught. So I'm going to end up getting 240 is equal to A naught. And that's it. So I have 240 grams initially. All right, now write an equivalent formula with C equals 2, which would solve problem A. So now we want to write one where C is equal to 2. Well, if this is 2, then this here, if we put this 2, then this will have to be negative, right? We'd flip this, so that would be like saying this here, if that was 2, that's 2 to the negative 1 is equal to 1 over 2. So I'm going to have to do this. We would have 60 is equal to A naught 2 to the negative 2. Just like that. Okay? We just have to put negative. Or in this case, we'd put negative exponent there. Okay? So, in this particular example, explain how the solution to problem A could be found without using a formula. Well, for this one here, all I do is I just look at it and I say, well, we want to find the original. We know it's half-life, so I just go halving. We're halving. And we halve twice, right? And I said that's equal to something multiplied by 60. So I just would halve it twice. So I'd have to go the exact opposite of halving, moving it there. So that is, so I'd have to go halving. And then eventually I could just go around that one. So this is half twice, so it'd be like multiplying that. So that's like saying 2 to the a, 2 to the 2, is equal to times multiplied by 60 will give me my answer. So I could just multiply 4 because I know it's half twice. That is one way of doing it. So then we just go 4 multiplied by 60, since it's half twice, is equal to 240 grams. Okay? So that's another way of doing it without using a formula. Well, good luck. Hopefully you understood this. If you have any questions, don't be afraid to ask me tomorrow.